Hello everyone, my name is Kartik Dalwadi, a postgraduate student at SEPT University. My student code is PCM24163. Today, I will be presenting my portfolio for our studio course titled Integrated Construction Practice. To begin with, this studio was built around understanding the shift from traditional construction practices to integrated beam-driven construction. Our study project was a G+35 commercial high-rise with four basements, a building type where coordination becomes extremely challenging due to dense service networks, multiple disciplines, and sequencing dependencies. To handle that complexity, we followed a full integrated project delivery framework supported by BEAM. This included preparing the BEAM execution plan and employers' information requirements for governance, using LOD/LOS frameworks for model maturity, running clash detection and resolution, generating automated quantity takeoffs, preparing 4D sequencing, developing 5D cost-linked simulation, and incorporating last planner system for both design and construction planning. Within this broader flow, my specific focus areas were stakeholder alignment, beam execution planning, quantity derivation for firefighting and plumbing, and the 5D simulation. The project is the prime commercial hub, a 35-story commercial tower in Ahmedabad. It includes four basements, a built-up area of about 64,000 square meters, and a total project cost of roughly 256 crore. The tower includes high-speed elevators, multi-level car parking, and premium commercial spaces. In our team, I worked as the firefighting consultant and beam coordinator, responsible for coordinating model exchanges, managing classes, and preparing the LOD 300 firefighting model. One of the key things I worked on was stakeholder alignment, because without clear communication, even the best beam model falls apart. For this, we followed a clear methodology. We first listed all the challenges, met the stakeholders, and ranked them based on impact and urgency. Once the priorities were set, we defined the project goals for ICP and prepared the EIR and BEP to establish a structured framework for the entire workflow. We identified a total of 33 challenges during the project. Using a structured risk matrix, we assessed probability and impact. The highest risk items were P5 project stakeholder coordination, E1 construction rework. These have both high likelihood and high impact, which is typical in large MEP heavy projects. Major design related risks included D6, revision delays, and D7 lack of clash detection at early stage. A large portion of the medium to high risk were related to coordination gaps, inconsistent updates, and ambiguous responsibilities. In a high-rise like this, where MEP system becomes extremely dense, the BEP is what prevents chaos. It is basically the discipline level agreement that keeps the project aligned. We prepared the beam execution plan along with the beam objectives and goals defined specifically for our project. The objectives on the focus on establishing a coordinated model-based workflow across all disciplines, improving accuracy in design and documentation, and ensuring that the project team works in a unified digital environment. The BEAM goals highlighted what we expected to achieve through this process: better collaboration, fewer clashes, streamlined data exchange, and a consistent modeling standard throughout the project lifecycle. We also set up model folders, versions, and naming standards so that one could accidentally overwrite files or model in wrong place. The common data environment was organized. Each discipline had its own folder, and inside that we kept versions clearly separated. This avoids the classic side problem where someone models on an overdated version. This slide highlights the overall BIM process mapping, which shows how information flows across design, coordination, and documentation stages. The mapping begins with each discipline developing their base models. These models move into the coordination cycle. Clashes are detected, comments are issued, models are reworked, and the coordinated model moves into scheduling, estimation, and documentation. This iterative workflow ensures that no model processes until spatial and functional coordination is validated. It also clearly defines when consultants interact, when modeling freezes occurs, and how updated information is fed back into the CDE. For LOD 300 modeling, I handle the entire firefighting system and plumbing, which includes sprinkler layouts, hydrant network, fire extinguishers, pipe routing, valves and accessories, soil and waste piping, domestic and flushing water supply, and sanitary fixtures. Everything is modeled to construction level accuracy with correct routing, spacing, and model ownership. This is important because LOD 300 is the first level where the model is actually useful for coordination and estimation. Model authority was also defined for each element, ensuring no discipline overrode another's components. Next is quantity takeoff, which was another major part of my work. We compared manual quantity takeoff with Revit-based quantity takeoff for the firefighting and plumbing systems. Here the table shows the quantity of 34th floor, whereas the graph shows the comparison of quantities of basement 1. We found a 0.5% variation for both the levels, and the reasons was Revit auto-generated non-standard pipe diameters and manual quantity takeoff couldn't capture hidden components. We can say that manual quantity can miss hidden geometry, but Revit captures everything. 5D simulation. For 5D, the baseline start was 19th July 2025 and baseline finish was 11th September 2025, but the actual start and finish were 27th August 2025 and 5th October 2025. From the schedule analysis, we identified the key reasons for delay. The major issue was the uneven level distribution. Excess manpower was allocated during the last 5 floors, which pushed labor costs higher than planned. Additionally, the RCC activities were targeted to finish before Diwali, but the sequencing didn't align with actual progress on site. This mismatch led to both time overruns and cost escalation, placing the project in an over-budget and behind-schedule condition. After analyzing the delay, we moved into the 5D simulation workflow. We exported the coordinated Revit model into Synchro, aligned it with the construction schedule, and linked each activity with its corresponding model elements. Once the timeline was connected, we integrated cost data to create a cost-loaded schedule with geometry, cost, and fully linked. Synchro generated a visual 5D simulation that allowed us to see how delays and resource mismanagement impacted the project in real time. On-vendor analysis, where we evaluated the project using CPI and SPI. The cost performance index helps us understand whether the project is under or over budget. A CPI value of 0.99, which is less than 1, indicates overspending. Similarly, the schedule performance index helps judge whether the project is ahead or behind schedule. And SPI of 1.07, which is greater than 1, indicates faster progress. The EVA graph shows how the planned and actual costs behaved through the project timeline. Early stages matched well, but later the actual cost curve rose above the planned cost, showing faster progress, cost efficiency, positive deviation from the baseline. This indicates well-managed execution in the later phases despite early delays. The completed 5D simulation shows the coordinated visual progression of construction with cost linkage. This simulation demonstrates how 5D BIM provides clarity in budgeting, sequencing, and resource forecasting, which helps in preventing overruns. This is where traditional practice falls short. You cannot visually see delays, overruns, or sequencing conflicts, but with 5D, everything is transparent. Conclude, here are the Key takeaways from my work in this studio. Stakeholder alignment is the foundation of successful integrated practice. A well-structured BEP and CDE eliminate confusion and ensure predictable workflows. Value 300 modeling adds real value to coordination and estimation. Automated quantity takeoff reduce human error and capture hidden elements. 5D simulation transforms decision-making, giving a real-time view of cost and schedule impacts. Integrated construction practices significantly reduce waste, rework, and miscommunication compared to traditional methods. Thank you.